So why didn't it work? I want you to show that there's some
Hello, everybody. Welcome back. All right, it has been 1 week since we last spoke, and we have 3 weeks to go. All right. So today, just before everyone arrives, I want to talk about our comprehensive exam. So your comprehensive exam will be on the last day of this class. It will be on a Wednesday, and it will be the same time as the lecture time. And the format will be multiple choices. And here is one sample. Let me see. Here we go. So you're going to get 40 questions like this. It will cover everything we covered in class, on the slides, in the textbook, and also additional readings. So please do not ask if a certain topic will be covered on Piazza. Well, I encourage you to ask anything you like, but I will not answer this type of question just to make sure you, well, for example, if I tell you something will not be covered in the class, probably will no one is going to read that part in the textbook. But for the textbook, just remember when we talk about all these different algorithms in class and also in on your slides, you don't have to read the ones that we did not cover in class. Okay, so if there's an algorithm X in chapter 3, although we covered chapter 3, but we didn't cover that algorithm, that's okay. It's not covered in the comprehensive exam. Are we good? Any questions?
How long will the exam take?
That's a very good question. I'm not sure because I don't have all the questions yet.
All right, thank you.
And there's a question, will it be on the Blackboard? Yes, the exam will be on Blackboard. You can use a calculator. You cannot use any other materials. It's closed book. Any questions for the exam? What would be the answer for your question, for this question? Anybody wants to try? All right, it's asking you about AGM, right? So if you read the textbook and also you come to the lecture, you should know about the AGM. So A, we cannot estimate the community detection result by directly finding V, C, M, and PC. Is it correct? So Christina says no. Why? Well, the real answer is this is correct. You can't. Because if you can, we are not going to cover big claim, right? So the reason why we cannot really estimate this is the search space is huge. Remember, you have to repeat doing this all over again. So there's no way you can find VCM PC, not even directly. All right, B, the community memberships of a node is determined by the parameter PC, where C is the community. True or false? Filana says false. Anybody? Great. Community membership is determined by M, and PC has nothing to do with that, right? So once you have the community membership, you have the PC for that community so that you can start to estimate. Great. C, when two nodes are not in the same community, the probability of their existent edge between these two nodes are controlled by a constant number. Correct or incorrect? This one is true. Great, because it's a tiny number, because if they're not in the same community, you're going to use a tiny number to indicate that the probability is very small. All right, D, the overall edge probability between two nodes U and V is as follows, where PC is a set of tiny numbers. True or false? D. Jin Chen says true. Zhen says false. False. Yeah, it's incorrect. Because your PC cannot be a tiny number. If your PC is a tiny number, that means you cannot really detect any community for a given setting, right? So then you know you will not choose E because you do have some true options. Okay, so this is your comprehensive exam style, and as you can see here, you just need to understand how the algorithms work. If you can do very well in the quiz, you will be able to do very well in the comprehensive exam. We usually have an average score of the comprehensive exam. We usually have 70 something. And I do have students who scored 100% for the comprehensive exam. Christina says, can we have some review sessions like this before the exam? Well, if we have time, I can go over all the topic in one lecture, but only if we have time. All right, so general statistics, we do have people score 100%, and we also have good students score very low in the comprehensive exam. So, but in general, it's about 70, 75 on average. So, and it's a normal distribution, which means it really can tell if you study your textbook and the slides and if you read the papers, okay? All right, any more questions about the comprehensive exam? All right, so let's continue on our topic.
Got a quick question. Do we have a quiz that Monday before the final exam?
Yes, we do have a quiz.
Okay, awesome. Thank you.
Yeah. So also one more thing I want to say is your TA's office hours. So today is Monday. We are going to have our quiz until 10 p.m. Sorry, not 10 p.m. Until 8 p.m. And from 8 to 9 will be Weiwei's office hour. 9 to 10 will be Minchen's office hour. So from this week, for the rest of the weeks in this class, you are going to be able to see both of your TAs on the same week. And we're going to offer at least, I think, 1, 2, 3, at least 4. Well, we're going to have 3 to 4 office hours every week. And I'm going to post their schedules on Piazza, but at least for today, 8 to 9 will be Weiwei, 9 to 10 will be Minchen. So if you have any questions about your homework assignments, please go to the office hours. All right, so finally we can start. And I just remember someone was asking a question on Piazza about how to estimate. Let me see. Here you go. How to find Mahalanobis distance between two compressed sets. Oh no, this way you know who posted. So Piazza is anonymous, but we can actually see your ID. Let me put the question here. Here's the question. So when we are adding points to the DS, we can use Mahalanobis distance, right? Because Mahalanobis distance is measuring the distance between a point to a cluster. So for comparing to CS, there are multiple ways you can do it. You can compare a CS centroid to the other CS, the entire cluster, or you can just combine them and compute the variance, see if you want to merge them. The question here is about, then how do we set the threshold? So as for many similar types of questions for data mining, you always take a small sample, you try it, right? So you take a small sample, you look at your CS, you say, hey, let's just use a threshold of X, and you see what's the result like. Then if you don't like the result, you improve your X, you can make it larger, make it smaller, and look at the result again. CS is not the outlying clusters. CS are the compressed set. That means they are not close to any of the DS, but they can be grouped together because they're near each other. The RS are the real outliers because they are not close to anybody. So when I say you need to empirically test this, I mean, you take small sample data, you set some threshold, you look at the result, and you see if you like the result or not. Then your question might be, how do I know if I like it or not? That will be your assignment, right? So you need to know if a certain a certain cluster structure is good, or if you want to increase your threshold to make it better, right? That's the assignment part. All right, so I hope that's clear. And now we're going into our streaming data lecture. Okay, we were somewhere here. Okay, I can start from here. All right, remember what we have been talking about, this AMS algorithm? The goal is to be able to estimate the second moment of a data stream. What is the second moment? Anybody?
Is that the distribution?
Right, some way to look at the distribution, right? So somewhere here, this is your surprise number, and it's sum of the squares. What is this MI? This is the frequency or occurrence of a certain type of element in your data stream. Okay, so this is cool. You need to, if you need to estimate it, sorry. If you really need to count it, then you have to generate a counter for every type of element in your data stream, right? You have to generate a counter for A and count how many times A occurs. So 1, 2, 3, 4, 5. You need to generate a counter for B and count it, and so on. The problem is you do not have that much memory space for all these counters. So our idea is we are able to use only a limited number of counters, and we are going to use this function for estimate. And last time we talked about this. We say, all right, this is going to have an expected number based on this function that will be the same as the summation of all the squares. And then you got your estimate. So today we're going to talk more about how this works, why this works. So your second moment is the summation of the frequency square, right? This is your goal. You want to estimate this. And say CT is the number of times an item at time t appears from t onward. Right? We looked at this before, and this is exactly how our random variable is recording the occurrence. For example, if you look at here, A, so C1 will be MA, right? This is the first time you look at A, and you're going to count the number of A's you have, so that'll be MA. C2, the second time you see A, that will be MA minus 1, and C3 will be B, and it will be MB. Okay, so the expected number of this function is equal to, first you do the summation, then divide it by n. Are we good with the definition of expectation? Why are we dividing this by n? Because it's expected. Yes, great, thank you. And also because when we divide it by n, because every timestamp has equal probability, and this is a discrete variable. So you can just divide it by n, okay? If they don't have equal probability to show up, you can use a probability number to weight the higher probability one and also sum up. All right, anyway, this is our target function, right? Remember when we say if you want to estimate it, you use this target function. And you take all this target function, you sum them up for every time step. Then you divide it by n. This is the expected number for the function we used for estimating the surprise number. But if we look at this function here, and also the way we calculate the expected number here, you can actually rewrite it. This is from time 1 to time n, and every time point, you do 2 times this time point's value and minus 1. And each time point, you are going to get this counter, right? C1 is MA, C2 is MA minus 1, and so on. If we don't do this, we can do this. We say for every X, right? For every different types of element in the data stream, we just sum this up. And what is this? Well, this is also 2C minus 1, but what is the C now? Because we know for every type of element, if you just record everything, you are going to have 1, 2, 3, right? 3 is here, and until eventually you are going to have MA for this element. Okay, so 1, if you take 2C minus 1, 2 times 1 minus 1, you have 1, 3, 2C minus 1, you 2 times 2 minus 1, you have 3, and so on. And eventually the last number is mx, so 2mx minus 1, right? So cool. We just rewrite it from for every time points to for every element. Okay. So this tells you can group times by the value seen, right? By the x. This is the time t when the last x is seen, the last one. Time t when the ct equal to 2, right? This one before the last one. And when the first x is seen, you are going to have mx. Okay. If we take this entire calculation we have right now, still your expectation, we just now do for each element. What is this? Well, this is actually 2x minus 1. We know this, and we know this is from x equal to 1 to mx, right? You can rewrite it to this, and eventually it becomes mx squared. But why? Well, if you look at this one is easier to read. This one works, but this one requires you to understand this through this. It's simple calculation, but this second one's more straightforward. So the same, we are going to loop through all the C's or all the different types of element and sum up all this 2C minus 1, right? Exactly this or this. But think about what is 2C minus 1? Well, 2C minus 1 is actually the summation of C squared minus the summation of C minus 1 squared, right? If you put these two together, it will be C squared minus C squared minus 2C plus 1, right? If you just merge these two terms, and it becomes cancel each other, becomes positive and minus 1. Okay? So now you know why this one is this one. Now it becomes very easy. If you look at this is actually just m squared. So why? Because here you are summing up from c equal to 1 to m. So the last term will be m squared, right? And this is from c equal to 1 to m. The last term is m minus 1 squared. And do we have m minus 1 squared here? We do, right? When c is equal to m minus 1, this number series has m minus 1 squared. So the difference between this term and this term is exactly m squared. Okay, so this part becomes m squared. at this. We just show that this part is this part and m squared, so m squared. All right. So now we have the second moment in expectation. What does it mean? This means if in the ultimate extreme case, when you have a random variable for each time point, you are going to get exactly m squared. You are going to get your surprise number. That means you are counting everybody, right? But if you don't have space to have a counter for every time step, but if you have large enough numbers of random variables, this will work because it's the expected number. So the conclusion, for estimating the kth moment, we essentially use the same algorithm, but we change the estimate. For k equal to 2, we use this function for our estimate because we show that in expectation, the summation of this becomes m squared. Okay, so I need to mute people. All right. For k equal to 3, we are going to use a different function to estimate it. But why is that? For k equal to 2, remember eventually we show this, right, for your number series, and we want to sum it up like this. And we show that this is the same as this, and it's the m squared. So we just need to be able to find a function. When you sum them up, this will become m cubed. Okay. So when k equal to 3, that means we want to estimate m cubed. We look at this, because if you have cube here and cube here, you're going to have m cubed, right? So c cubed minus c minus 1 cubed is this. So this becomes our function for estimating the third moment of your number series. And because in expectation, the summation of this will be m cubed. So in general, if you want to estimate higher order moment, you just use this function to help you estimate, right? Remember when we have square, square and square. When you have cube, you have cube and cube, and that's it. So in practice, we are computing this for as many variables x as you can fit in the memory, and this is because you only have the estimation when you are in expectation. That means you want to have lots of random variables so that you will be able to achieve that expectation. But once you have them, you are going to average them in groups and take medians of the average, exactly what we did before for which one? We were estimating something. Oh, that 2 power of r, right? Remember, number of distinct element in a stream. But what will be the problem? The problem here is the stream never ends. In all our algorithm, the algorithms we just introduced, we assume that there was a number n. This will be the number of positions in the stream. But in reality, the stream will go on forever, and n is a variable, not something that we could estimate, right? And this n variable is the number of input we have seen so far. So how do we do this in practice? So when you do have a stream that never ends, the variable x has n as a factor. You're going to keep n separately. You hold the count in x, right? Exactly like what we did, but you also use a variable to accumulate for n. Suppose you can only store k counts, k random variables, you need to store some away, right? Once you see the stream is growing, you have to store some of the variable or counter away. And our goal is to be able to estimate the second moment of a stream of length n. And this n is a variable because when you have a new element, it will change size. Each starting time t is selected with some probability k over n. And it will be our fixed size sampling, right? Our reservoir sampling. You choose the first k because you can store k variables. You choose the first k for k variables, then you keep recording. When the new element arrives, n is larger than k, you will choose it with some probability k over n. If you choose it, you're going to throw one of the previously stored variable x out with equal probability. So this way you have a systematic method to sample your stream and generate the counters. Let me show you one example. Here. So remember this one? Let's say here we have we can store 3 random variables. And so there's a question. Is this the reservoir sampling method we mentioned before? Yes, exactly. That's the reservoir sampling, fixed size sampling. So let's say this is the stream and you want to estimate your second moment. You only have 3 random variables you can store. You begin from, let's say here, this is the first element you see, right? You haven't seen all others yet. When you see the first one, you just say, all right, I am going to have a counter CA because I can store 3. Second one comes, you store it again, CB. The third one comes, CC. Fourth one comes, you don't have enough space, right? Because you can only store 3 variables. So the third one comes, you are going to say, now your n is 4, your sample is 3. I will give this probability to for initiating a new counter here. And say if you do initiate a new counter, CB, you're going to pick one of these old counters with equal probability and throw them away. Let's say you pick the first one, then you're going to throw this away, right? Then you read another one. Now you have to decide based on the probability again, but now your n is what? 1, 2, 3, 4, 5. And your sample size is still 3. So based on a probability, you would choose if you want to retain D. If you do, you say CD. Then for this 3, you're going to pick one to discard randomly. So maybe this one and continue. Okay. So this way, your n changes every time when you see a new data element and you keep a fixed size sample. All right. Awesome. Our last algorithm for stream data is sliding windows. So sliding windows is a very useful model for stream processing. In this type of stream processing, we're looking at a window of some length, let's say length n, and these are the n most recently received element, right? You only care about this n, you don't care about the historical data. But some interesting case here is your n could be too large. Let's say your n is 1 billion, your window is really large, so you cannot really store the entire n data points in your memory or even on the disk. You have to throw away something. What would be an example? In Amazon, let's say for every product X, we kept this 0-1 string of whether the product was sold in the nth transaction, right? So every product, you are going to have a bit to indicate if it's sold. And it's streaming data because all the transactions are real time. And we want to answer queries such as how many times have we sold X in the last K sales? And K sales, this K can be 200 or 10,000, depends on the length of the window you are looking at. And different stakeholders, different people in the company might also have a different idea of the K. For the K they want to ask. Right, let me restart my PowerPoint. Something wrong with my PowerPoint. Give me 1 minute. Okay, should be fine now. All right, so let's look at an example. Wait. How about this? Let's take a break for 10 minutes and I will fix this problem. And when we come back, we are going to continue on this. So 10 minutes, come back at 45. All right, I'm back. PowerPoint is back too. All right, so let's continue. So here shows you an example of a data stream and a sliding window on this single data stream. You can see as time goes by, the window will move, right? This old element will be discarded, it's outside of the window, and the new element is added within the window, okay? But this data stream actually show you the future. In practice, you are not going to see this. You don't know this. And this is your window. When the time goes by, you start to see more element and you are going to discard the last element in your window. So this is a data stream and this is a fixed size window. So the problem that we want to solve, this is not like Shingo. Well, yeah, Shingo is a sliding window as well. But for Shingles, you do have the entire sentence or entire document. But here you do not know about the future. And that window could be really huge, 1 billion bits. So the problem is, let's say, given a data stream of zeros and ones, we are only consider zeros and ones in this case. We want to be prepared to answer queries such as how many ones do we have in the last n bits, right? This n is your window. Some obvious solution is we can store the most recent n bits, right? If you have the memory space, you just store them. When the new bits comes in, you just discard your n plus 1 bit because it's outside of the window and you are done, like this. Suppose your n equal to 6. This part is the data stream that you are going to store always. The real problem is, what if we cannot afford to store n bits? Because you cannot really get an exact answer without storing the entire window. If you don't have the entire data set, you cannot answer that question, how many ones do we have in this window? If we cannot afford to store them, but we are happy with an approximate answer, how do we do that? Let's see the first attempt, simple solution. Question, how many ones are there in the last n bit? This is your n window, this is your data stream. The first solution is uniformity assumption. This doesn't really help us to solve the problem, but just want to show you. You can maintain 2 counters. The first counter is S. This will be the number of ones from the beginning of the string, like how many ones have you seen so far? And you can maintain a second counter, Z, the number of zeros from the beginning of the stream. When someone asks the question, how many ones are there in the last n bit? You compute the ratio, right? This is the 1 versus 1 plus 0 ratio, and you times n, because you are looking at the last n bit. This could give you an answer, but this answer assumes that your data is uniform. That means this 1 and 0 ratios does not change over the entire data stream, right? Because you are recording these numbers from the beginning of the stream. But your stream is usually non-uniform. Think about Amazon transaction, for example, morning, night, it will be different. Different days will be different. Weekends will be different. Holidays will be different. So if the stream is non-uniform and the 1 and 0 distribution change over time, you cannot really use this. And you cannot really handle various k, because no matter what k you have, what window sizes you have, you are going to have always the same ratio, right? You assume this uniform ratio. So this is not going to work. Our solution is DGIM. This DGIM solution does not assume uniformity in your data stream, and it requires very tiny memory footprint. It will store big O log n times log n bits per data stream. This is the only data requirement you need. And we rewrite this into this. So just to make sure that you know this is a square, not base 2. Okay, so it's log n times log n. This DGIM solution gives us some approximate answer. For that, how many ones do you have in the last n bits? It's never off because it's an approximate. It's important that we know the error bounds. The solution never off by more than 50%. This means if it's overestimate, it will not overestimate more than 50%. If it's underestimate, it will not underestimate by 50%. The error factors, this 50%, can be reduced to any fraction larger than 0. You cannot have 0 because you are not going to store all the bits. With more complicated algorithms with proportional more stored bits. So we're going to look at the most efficient one, but the error margin is not small. It's not huge as well, but it's not small. So DGIM algorithm, the storage requirement is log n squared. The error rate for the query is smaller than 50%. For example, if your true number of ones is 100, this is true number of ones in the last n bit, your estimate will be between 150 to 50, okay, within this range. The key idea of this DGIM algorithm is we're going to partition this window n into a small set of buckets. The word buckets is probably the most used word in this semester. We are going to remember the count for ones because we're only counting ones. The count for ones for each bucket. We're going to use the count to help us approximate the answers to our queries. Remember the queries. The query we have is how many ones do you have in this n window. So let's look at the memory requirement, and we are going to look at how the algorithm works. So first, timestamps. Each bit in the data stream, remember we are working on bit stream with zeros and ones and zeros and ones. Each bit in the data stream has a timestamp, and we can start the timestamp with 1, 2 until n. The way DGIM record the timestamp is you take a real timestamp. Let's say this one is April 12, 5 p.m. Right? You can take this, convert this to the Unix time. Then you have a really long string or long number, and you take that long number. You do a mod n. This is your window size. Then you can represent any relevant timestamp in your window with log 2n bits. Right? Once you have the timestamp, what are the other things you want to record? In the buckets, remember we're going to use buckets to record how many ones we have in each bucket. In a bucket, each bucket represents a sequence of bits in a window. The buckets does not store the actual bits because we do not have the space to store them. The bucket will store a timestamp to tell you when the end time for the bucket, and also the number of ones in this sequence. Right, so this is like a counter, only count ones. So the timestamp only store the end time. This help us to understand, help us to figure out if that bucket is still within your window n. The bucket size has a special rule. The bucket size is number of n's in the bucket, but we store them always in some power of 2. That means we store 1, 2, 4, 8, 16, and so on. I'm going to show you some examples of this, so don't worry if you don't get it right now. And there are some rules about this bucket. Either 1 or 2 buckets with the same power of 2 numbers of ones. Buckets do not overlap in the timestamp. Buckets are sorted by sizes. Buckets disappear once their end time is larger than the end time unit in the past. That means it's over the window. So let's look at this bucket. This is your data stream. 1, 2, 3, 4, 5, 6 bucket. And if you look at here, this bucket store 1, so the counter will be 1, and 1 is 2 power of 0, right? So we are going to store 0 because we know that it's always 2 power of something, so we store 0. The second bucket has 1, the counter is 1, so we store 0 again. Now you have a 0, you don't care because it doesn't have 1. Now you have this one has a 1, so the counter is 2. You have 2 ones, and 2 is 2 to the power of 1, so in this bucket you store 1. For this bucket, you store 1, 2, 3, 4. Counter is 4, 2 power of 2, so you store 2, and so on. Okay, so you can see that all these buckets, they do not overlap each other. Also, you have small count and on the right side, and you have larger count on the right side. Sorry, larger count on the left side. So let's just revisit all these rules here. So properties of the buckets, either 1 or 2 buckets with the same power of 2 numbers of ones. If you look at here, you only have 2 ones. Here you have 1 size of 2, which is okay. You have 2 size of 4, you have 2 size of 8, and so on, right? You will not have 3 size of 4. This property is important because we are going to rely on this to help us calculate the error bound of the estimate. Buckets do not overlap in timestamps. Buckets are sorted by size. You have small ones on the right side. You have larger ones on the left side. So how do we generate the buckets? So far, I told you about all these buckets and their properties, but I haven't told you how we update or generate all these buckets yet. So when a new bit comes into your data stream, we are going to drop the last bucket if the last bucket has an end time prior to n, right? Because when you have new data coming in, you push the older bucket, and it could be that your old bucket got pushed out from n. Now you have 2 cases. Say the latest bit that you received is 0 or 1. If the current bit or the latest bit is 0, there's no other changes because we do not record 0, so we can continue to receive more bit. If the current bit or the latest bit is 1, we are going to create a bucket of size 1 to record it, right? Because we want to record every 1. And the smallest bucket that we can have is size 1. That will be the bucket on the right side of your data stream. And in this bucket, the end timestamp is your current time, right? Because that's the end time for the last bits in a bucket, which you only have 1 bit. If there are now 3 buckets of size 1, remember we say we can only have at most 2 buckets of the same sizes. If you have 3 of them, that means you already have two buckets of size 1 before you see the new bit. We can combine the oldest 2 buckets into buckets of size 2, and if now there are 3 buckets of size 2, you combine the oldest 2 into buckets of size 4, and so on, right? You maintain the order, and also you maintain the fact that you can only have at most 2 buckets of the same sizes. If this is still not clear, let's look at one example. Example is very easy. So this is your data stream. Say you already generate some buckets, and when a new bit comes in 0, are you going to do anything to update the buckets? So there's a question, the size of buckets are fixed. The size of the buckets, I assume you say this, when you say size, you mean the length of the bucket. Yeah, it's not fixed, but the count is, the rules are on the count, not on the size. All right, so Sumi, Tingwei, and Zun both says no. Great. We are not going to do anything because we don't record 0. When you have a 1 comes in, you create a bucket. This is bucket of counter 1, so it's 2 power of 0, And now suddenly you have 3 to power of 0, right? What do? You're going to merge these two. Can you merge these two? If you merge these two, you are going to have a bucket of what? 2 power of 1, because then you are going to have how many ones here? 2 ones. If you merge this 2 on the right side, you are going to have a size 2 here, size 1 here, and size 2, right? This violates the property of the buckets, that the bucket should be in order. So you're going to merge this 2. The way you merge it is just like this. And this is exactly why your bucket length in bit can vary, because the distance between 1 bits can vary. All right, so great. Now you have 1 bucket of size 1, 2 of size 2, and you do not touch anything else. You have another one comes in, create a 1. Now you have to merge this 2, becomes this. And what do you do next? Next is you're going to merge this into a bucket with count 4, right? But if you merge it with count 4, you already have 2 count 4 here. So you're going to merge it into count 8. And then you have 3 count 8. You're going to merge them into 16 and so on. Then you are done. So this is how you update and generate the buckets. Okay, this is actually the entire algorithm. But what we really care about are 2 things. First, since this algorithm tells all the properties of the buckets, how do we use this to estimate the count? And how do we know the error is never more than 50%? Second, for this method, what would be the memory consumption? So question, why is there a bucket of size 3? Where do we have the bucket of size 3? The size is based on the number of ones, not the length. Contain 2 ones. This one is 2. Right? This is 2 power of 1, and you actually record 1. Okay, cool. All right, so let's look at some analysis of the algorithm. For the bucket, a bucket in the DGIM method is a record, right? You're going to record something, and you're going to record the timestamp of its end, because you want to know if this bucket is still within your window. And we know this is log2n bit, right? Based on the way you create the timestamp. The number of ones between its beginning and end, right? No matter the size of the length of the bucket is, we only record the number of ones in the bucket. And the memory consumption of that is log2, log2n. So why do we have log2, log2n? Well, log2n is the maximum number of bits in a bucket of size n, right? Because your window size is n, so you take n and you do a log2, that will be the maximum number of bits, assuming that window is as large as assuming that bucket is as large as your window. Because when we look at all this memory consumption or complexity, we are looking at the baseline cases or the worst case. So to store x, we need to store log2x bit, and x is in the worst case. Constraints of the buckets, number of ones must be power of 2, so that you can take the number of buckets, the number of ones, maximum number of ones you can have in the buckets. You do a log2, then you know how many bits you need to store it, right? So remember this. When you have a bucket and it has a count of 2, you do not store 2, you store 1. Because we know this is always 2 power of something. And if you have 10, 40, 2, you store 2 to the power of 10. No, 1024, sorry. Right? It's 2 power of 10, and you store what? 10. So how many bits do you need to store 10? It will be 10 log 2. Okay, cool. So we know there are some timestamp we have to store. We have also need to initiate a counter for each bucket to store the number of ones. And let's look at these two numbers. For the timestamp, in your window, you are going to have timestamp from 0 to n-1, right? Because you're going to take that Unix time and do a mod n to give you a number, show you the order of that buckets in your window. And if we know that the largest number will be n-1, you only need log to n bits to store this timestamp. Great, covered. How about the number of ones? Well, we know in a bucket, you are going to store 2 power of j. This is your, this j is something you really record for the buckets, and 2 power of j is the number of ones in that bucket, right? So what would be the maximum number of ones in the buckets? Assuming your bucket is the same size as your window, and every bit in your bucket is a 1, this 2 power of j will be smaller and or equal to n, right? N will be the maximum number of ones you can have in a bucket. So if we know this, then we know that the j, the number that you're going to store, is smaller than log 2n. And since you're going to store j in bits, you know that you need this number. You take log 2 of, here is j, this is j, log 2j. You need this number of bits to represent j. And this number is actually too small compared to your timestamp, so you actually get something free. You only need to store, well, you need to store both of them, but your counter for j is too small. We can ignore it, and eventually each bucket require only this here. So look at this. This is not equal. This means this is approximate complexity, because it's big O(n) plus this log 2 log 2n. This is for timestamp. This is here. This is for timestamp. This is for your counter. And we say this is too small. All right. So still storage requirement for DGIM at most 2 times j buckets, right? We know that for each count, we can have 2 buckets, two of the same size. And if you have 2 times j, they're going to have all these different sizes, right? 2 power of j, 2 power of j-1 till 1. So there's a question, the second log 2 is because of binary storage. Yeah, because we are calculating how many bits you need. So that's why here, also here. Right, n is a number. How many bits do you need to store this number? You take a log 2. All right, so at most we are going to have 2 times j buckets, the size of the largest bucket. We know this from the last slides. So we know j is smaller or equal to log 2n, and 2j is smaller or equal to 2 log 2n. That means what? Well, 2j is the number of buckets we have, and from the last slide, we know that for each bucket, this is our storage requirement, right? And this is for each bucket. And how many buckets do we have? We know that at most we are going to have 2j bucket. And what is j? Well, maximum j is this. So 2j becomes, well, this is j, so times 2 times this. Okay. All right, very important. Let me say this again. This is the memory requirement for each bucket. This is the maximum number of buckets you can have. It's actually 2 times this, but I will tell you why we ignore 2. All right, when you have this, this becomes log square n. This log 2n times log 2n. And why do we just ignore 2? Well, because you have a big O notation here. You only care about this. Constant scalars, you can usually ignore it. So this is our memory consumption. Pretty cool, right? Based on what you see so far and based on all the constraints about the buckets, this is what we can achieve. We can use a tiny space to store your important information about your data stream and can make an estimate. But how do we use the bucket for our query? To estimate the number of ones in the most recent n bit, we are going to sum the sizes of the buckets, but the last. For the last one, we're going to take half of the size and sum them up. So remember, we do not know how many ones of the last buckets are still within the window. I will show you here. So say this is your window. Your window cut through here, right? If your window is at this location, we can give you an exact answer because we know all the buckets are here. However, it's very common that your window will not just start at a bucket. It usually cut through a bucket. So when it cuts through a bucket, when we want to answer the question, how many ones do you have within the window? We just sum this up, right? Sum up the places that we do have an exact answer, and we take half of this. We just take, so for example, here you will have 16. So you just take summations from here and you just add 8. And that's your answer, or that's your estimate. Okay, cool. Now you know how to query it. But we still don't know why our error rate is within 50%. So let's look at how good is the estimate. Suppose the number of ones in the last bucket is 2 power of j. Okay. Case 1 is when your estimate is smaller than your actual value of c. So this is your actual number of ones in the window. What would be the worst case? When estimate is small, we want estimate to be very, very small and actual value to be very, very large to see the worst case, right? And what would be the worst case? In the worst case, all the ones in bucket B are actually within range. So let me go back to here. So that means you do have lots of 1 here, and you all have all the zeros here except this last bit. Right, because every bucket, you can see it will start and end at 1. Well, this is because when you merge them, you're going to have ones on the either side. You can work on one example and you will see that's not very important. But here, the worst case is you have all the ones in bucket B, last bucket, are all within range, but when you do the estimate, you only take half of them. Right? So your estimate will miss at most half of this 2 power of j. So half of the 2 power of j would be 2 power of j minus 1. This means if your actual value is larger than 2 to the power of j, we missed no more than 50%, right? Because you underestimate. If your c is larger than this, you're okay. And 2 power of j minus 1 is smaller than 0.5 times c, right? This is half of c, and this is your error. The estimate missed, and we want to show this it's smaller than 0.5 of c. So what would be the minimum of c? For your actual value, you are going to have at least 1 bit from B, right, for the last bucket. You have one, you have one, you have the window end here, and you do not know anything in between. Only thing for sure that you know that you're going to have at least one bit from B, which is this one, because this can all be 0, plus at least one bucket of all the lower power. So everyone here needs to be counted. And we know that this is ordered, and you need to have at least one bucket for each lower power, right? So that would be 2j minus 1 plus 2j minus 2, because your last bucket is 2 power of j, and until you have 1. So if you sum up the series, is 2 power of j minus 1 here. Okay, cool. So your C is larger or equal to the minimum value, which we just derived, which has a 1. This one is the last bit from your, the rightmost bit from your bucket B. And this is the summation of at least one bucket of the lower powered, and cancel each other. Your C is larger or equal to 2 power of j. Right, cancel each other. C is larger or equal to 2 power of j, and you missed at most 2 power of j minus 1. That means your estimate missed at most 50% of C. And your estimate is at least 50% of C in the case when your estimate is smaller than the actual value. So let's look at the second case. In the second case, suppose the number of ones in the last bucket is this again, and the estimate is larger than the actual value C, right? Last case we were saying it's smaller. The worst case is only the rightmost bit is within range. All others are not within range, so we overestimate. We take half of it. Only one bucket for each smaller power, and in this case, when you count the minimum C, it'll be 1, right? Rightmost bit from B plus everybody from the lower case. Only one bucket becomes this. Remember this is here. So your minimum C is 2j. Your estimate is 2j minus 1, right? This is your last bucket, because your last bucket is 2j. 2j divided by 2 is 2j minus 1, plus everybody else, right? The ones that lower orders that you do have an exact answer. This becomes this. And this is your C. So your estimate is no more than 50% greater than C, right? You have a C minus 1 plus this. This is your estimate. And if it is 50% greater than C, you are not going to have minus 1. It will be 2j plus half of C. Okay. So great. For second case, we also show that the estimate is larger than the value of C. So some extension, that's everything you need to know about the algorithm. Some extensions, can we use the same trick to answer queries? How many ones do we have in the last K when your K is smaller than N? Well, you can actually do that by finding this K, because you do have all the buckets. You just cut it. Then you just sum of the sizes of the most recent buckets plus half of this. So the algorithm is very flexible. You can have different Ks, and you are able to answer all the questions about how many bits you have in a certain length with error less than 50%. All right, so that's it for data stream, and this is your last assignment. Last assignment is actually much easier than all other assignments. It's just to help you get through all these difficult times. All right. Wait, someone say something. Okay, so just in case you were not here at the beginning of the lecture, we are going to have your office hours for your TA, Weiwei from 8 to 9 p.m. and Minchen from 9 to 10 p.m. today. All right, you can start your quiz. You can have until 8 p.m. to work on your quiz. Good luck. And I will see you on Wednesday.
Okay, time's up, and I'll end the session.